Our little journey through classes of spaces with increasingly more features and increasingly better properties now culminates at the so-called Hilbert spaces in section 2.4. They are named after David Hilbert, another great mathematician of the 20th century, and that's his picture. Before we can define Hilbert spaces, we again start at vector spaces. So let X be a vector space, so it has an operation plus, operation alpha times, as usual, where again alpha comes from either the complex or real numbers. Let's say it comes from a field F that is R or C, and we will write alpha conjugate and mean either alpha or the complex conjugate if F is either the reals or the set of complex numbers. So the last essential feature that is still missing is a so-called scalar product. We know that from R to the n. Scalar product shall be denoted by brackets like these, and it has two arguments that I'm replacing by dots here, and it gives you a number in this field F, and the dots are filled with elements from our space X, so vectors, right? For a scalar product to be called scalar product, we need four properties to hold, and these are, well, you should know them from your linear algebra 1 or 2 course. Let me just label them by S1, which is the first axiom for scalar products. And this one means that the scalar product of any vector with itself is real and positive if the vector is not the zero vector. Second axiom says that it has to be compatible with alpha times in the following sense. So the scalar product of alpha times x and y is just alpha times the scalar product of x and y. The third axiom says that it has to be compatible with plus. So let me say I have x plus another x, let me call it x tilde. And then scalar product with y just decouples into x comma y plus x tilde comma y. And the fourth and final axiom of scalar products is so-called symmetry. If you flip x and y around in the scalar product, then you get almost the same, well, up to complex conjugation that, as we agreed before, you can ignore if we're talking about real numbers. So let me just name these. So the last one is called symmetry. This one is called additivity. This one is homogeneity. And the first one is called positive definiteness. If you look at the first axiom as 1, then you might wonder, well, what if x equals 0? That is quite clear from the second axiom, so let's just remark. If you apply S2 with alpha equal to 0 and y equal to the 0 vector, then you would get that alpha times x, that is then 0, comma y, that is also 0, would give you alpha, which is 0, times x comma y, that is 0, but no matter what that is, you would get 0. So indeed, the result is 0 if x is the 0 vector, and it's positive if x is not the 0 vector. So sometimes you read S1 in this form also. As a first example, let's look at f to the n, which is either r to the n or c to the n. And we all know how to choose the scalar product in this case. You would probably take something like x1, xn, comma, y1, yn, and define this as x1, y1 plus and so on, xn, yn. Well, at least that's what you do if these vectors are both real. If they are both complex, then you should put conjugate complex signs over the entries of the second vector in your expression here on the right. Of course, these only make a difference in the complex case, but there they are important. Let's restrict ourselves to checking positive definiteness, which is S1, so we can see where these complex conjugate bars are important. So you plug the same vector x1, xn in both slots of the scalar product. And by the rule that you see above, you have just x1 complex conjugate plus and so on, xn complex conjugate. And of course you remember that for complex, but of course then also for real numbers, this is just modulus x1 squared, and this would just be modulus xn squared, and that would clearly be positive if x is not the zero vector. So as soon as one of their components is non-zero, then this would be positive. The other axioms S2, S3 and S4 also hold, and you can check this very easily. Without those complex conjugate signs over the YNs, our axiom S1 would go terribly wrong for vectors like, let me take 1i, in which case you would get 0 as a scalar product, although this is clearly not the zero vector, or try I, in which case you would get -2, which is clearly not a positive number. One can carry the same idea over to infinite vectors, so let's go to sequence spaces LP, and let's be careful. Let me write L2, and we put the scalar product of x1, x2 and so on, comma, y1, y2 and so on, to pretty much the same expression that we saw before. So this is x1, y1 bar plus x2, y2 bar plus and so on. So this is an infinite series, and one can show that because we're putting this 2 here, this is going to converge. Checking the axioms S1 to S4 can be done just like in the previous example here, so let's not do that. And as a next example, let's look at the function space. Let's take the continuous functions over an interval from A to B, and let's put f comma g for two such functions equal to, we essentially do the same thing, so we take data from the first and conjugate complex of the data from the second, multiply and add up. But because for these functions over the interval from A to B, there's too much data for a summation sign, so we need an integral sign. So the integral goes from A to B, and we integrate over f of x times g of x, and again put the complex conjugate bar over the second. And also here it's very straightforward to check that the axioms S1 to S4 hold. If we're looking back at the definition, then maybe you're wondering whether that definition is a little bit unfair to the second argument of your scalar product, because compatibility with multiplication by alpha and addition is only enforced in the first component of your scalar product, but not in the second. Well, there's no reason to worry about this. We can show that similar things also automatically hold for the second component, and that's because by S4 you can simply flip around, make your first component the second and the second the first, and then apply the rules in the first component, which used to be the second, get plus out and flip back. The only difference is that your little alpha becomes alpha bar. So if we try this computation, so we look at x comma alpha times y, then we observe that by the fourth, so by symmetry, S4, is that supposed to say, we get alpha times y comma x, but with a complex conjugate bar on top. And now by S2 you can get the little alpha out, y comma x, but you still have your complex conjugate bar on top. And now you see that this is alpha complex conjugate times y comma x bar, and then by using 4 again you can flip back. But you see that the complex conjugate bar doesn't go away in your alpha. So indeed, homogeneity works a little bit different in the second component than in the first, but additivity is just the same.